Okay, let's get started then. So, we left off doing the titration of acetic acid. And then we got some points here. So let's go ahead and do some more calculations of these points. Some of these points, like there's the half equivalence point, the 1/4 equivalence point, 3/4, the equivalence point itself. Equivalence point, we've just neutralized it so we have the right amount of everything. And then two more, the 1/11 and then the 10/11 here. And this region here is called the buffer region. It's called the buffer region because of the product it makes. When you have incomplete neutralization, so we have acetic acid being neutralized with sodium hydroxide. That means that the limiting reagent is sodium hydroxide here, and so we'll have some excess acetic acid and some sodium acetate left over. And so from here to here, we aren't completely neutralizing the acetic acid. Once we hit here, we've neutralized all the acetic acid, and so we're just left with sodium acetate salt. Sodium acetate here. And so this is the buffer region because the buffer system consists of unneutralized acetic acid and sodium acetate, which is the product. So we have some reactant left over, and then we got some product that formed. And so this is why this is called the buffer region here. Over here, we're going to have the excess sodium hydroxide now. Because once we pass the equivalence point, we have more sodium hydroxide than we need. Not all of it's going to be reacted. And we'll have the sodium acetate still present. And so we have a strong base and a weak base type solution that's left here. And so the different parts here of this, we have the just the acetic acid here. We have the salt here, and then we have the excess strong base, weak base.
The y-axis pH.
Y-axis is pH. X-axis is what? Milliliters of NaOH, usually. Now, when we're just right here, we've neutralized practically all our acid, and so very little acid remains. And so pretty much it's just a tiny bit of acid and mostly sodium acetate here. So we usually have to use ice around this region here. Because as we get close to the equivalence point, either the excess reagent on this side or the reactant on excess sodium hydroxide on this side, excess acetic acid on this side is very small. All right, the same thing goes here. We're going to have very little sodium acetate here, so we'll have to do an ice table for that too. And so just that big strain. Now, normally the Henderson-Hasselbalch is good for what? A buffer, and a buffer range is from what to what, typically? pKa plus or minus 1. Well, that's for a buffer if you want to use it. Now, if you want to just use the Henderson-Hasselbalch, the Henderson-Hasselbalch can span a wider range, more so. And so we use the Henderson-Hasselbalch over a much wider range. Like this. But if we're really thinking about the buffer region, then at the 10/11s, we have a pKa plus 1 pH. At the 1/2 equivalence point, we have the pH is equal to the pKa. And at the 1/11th, we have a pH equal to the pKa minus 1. And so the actual buffer region is this flatter part here. But once we go beyond, let's say pKa plus 1.5, pKa plus 2, we're still going to use the Henderson-Hasselbalch, but we really wouldn't call it a very effective buffer because the pH is going to change more dramatically. And the same thing below here, although there's not much room below here. All right, so let's do some calculations just to illustrate some of these points. And so one calculation we'll do is, let's see, we already did this one, is that right? And then at 5 milliliters, what do we expect to have? The half equivalence point. And so the half equivalence point, do that calculation here, and just to show how this works. So at the half equivalence point, I have my 10 milliliters of acetic acid. What was the molarity on this? 0.100 molar? Okay, and then what I'm going to do is I'm going to add 5.00 milliliters of sodium hydroxide. We'll keep this to 3 sig figs. Here, to make it easy. And so we'll do our step A first. Step A would be solution dilution. And so the total is going to be 15.0 milliliters. And we'll calculate the new concentration. Leave that out. So,
0.1 molar?
I'm sorry?
Had they both 0.1 molar?
Yeah. They're both 0.100 molar. To keep the numbers simple. So the new concentration of sodium hydroxide is going to be, what is it, 5 to 10 dilution? No. So 5 to 10 dilution of 0.100 molar, which gives us what? Oh, 5 to 15, sorry. 5 to 15, which gives us 1/3. And so it's going to be 0.333.
130.
Hmm?
It's 130, not 1/3. So it's 0.
0.0.
Yes.
Okay. 0.0333 of 3 molar. All right, now the concentration of the acetic acid is going to be a 10 to 15 dilution of 0.100 molar, which is going to give me 2/3, right? 0.0666 molar. But we don't want to round these. They'll just lead to round off error. And so here we'll take acetic acid plus sodium hydroxide. We take the strongest acid plus the strongest base. This is going to give us sodium acetate plus H2O liquid. Setting up the table, our acetic acid is 0.0666 of 6 molar. So sodium hydroxide is 3 molar and 0 molar here. Now, what is the change going to be? Well, it depends on the K. The K for this is
Very, very low.
very, very large. And so we have this acid-base reaction. We're going to lose 0.0.
I think you missed 10 with the sodium hydroxide.
Okay. 0.0333 of 3 molar minus 0.0333 molar and plus 0.0. And so at equilibrium, we're going to have 0.0333, 3 molar, 0 molar, and 0.0333, 3 molar. And so if you look at what's left over, if we take the strongest acid and the strongest base that's remaining, that would be acetic acid and sodium acetate. Well, acetic acid plus sodium acetate yields sodium acetate and acetic acid, so nothing's going to happen there. But you should recognize this mixture as a, yeah, so this is a Henderson-Hasselbalch buffer. And so the pH here is equal to the pKa plus the log 1, which means the pH is equal to the pKa. All right, so we can do a shortcut. Since we know we're in this buffer region, this is a shortcut that we can do. We just look at what equivalence point we're at. So we'll start off with the, how about the 1/11th, or no, let's start off with the 1/11th equivalence point. Example, the 1/11th equivalence point. Well, how did I come up with the 1/11th? Well, you'll see how I came up with that here. Because at the 1/11th equivalence point, what this means is I've neutralized how much of my acid? 1/11th. You know, at the half equivalence point, I've neutralized half of it. At the full equivalence point, I've neutralized all of it. And so the 1/11th is I've neutralized 1/11th parts of acid. Therefore, 10/11ths, right, good. 10/11ths remains all right, so this 1/11th that I've neutralized, and this 1/11th that I've neutralized becomes product. Sodium acetate, converted into sodium acetate. All right, so therefore the pH is equal to the pKa plus the log of, now I have 1/11th sodium acetate and 10/11th acetic acid. And so you see the 11ths will cancel out, and we get that this is equal to the pKa plus the log of 1/10, which is equal to pKa minus 1. That's how I got that. The 1/11th is a little bit awkward. That would be 1/11th of 10 milliliters. So at the 1/11th equivalence point, we have 1/11th of 10.0 milliliters, which would be a full, what we call a full equivalent of base here. All right, likewise, we can do because of the symmetry, let's do the 10/11ths equivalence point next. Equivalence point means this. It means that 10/11ths was converted into sodium acetates, and 1/11th remains unreacted acetic acid. And so I only have 1/11th part of leftover acid. So therefore the pH is equal to the pKa plus the log of 10/11ths over 1/11th, which is the log of 10, which means that the pKa plus 1. And so this is how we can get these points very quickly. The pKa minus 1, pKa plus 1. All we have to do is do this. We have to take 1/11th of the full equivalent here, and then over here we take 10/11ths of the full equivalent here. So 10 elevenths times the equivalence point, which would be 10 milliliters. Equals 10 elevenths times 10.0 milliliters. You know, the amount that it takes to get the equivalence point depends on, you know, the amount they start with and the concentrations. I just picked the easy numbers, you know. I picked easy numbers because it's 10 milliliters of acid being titrated with base of the same concentration. So the numbers were easy to predict, but sometimes they are a little bit more tricky to predict. All right, why don't you calculate the pH here at the 1/4 equivalence point. So the pH is equal to the pKa plus or minus what? At the 1/4 equivalence point. Can you calculate that? And also tell me what the volume should be. Does somebody have it? What is it? Okay, pKa minus 0.477. That's correct. Over here, you know, at the 3/4 equivalence point, what is it going to be? It's going to be pH is equal to the pKa plus 0.477 because the fraction will just be flipped over. So these points we could get very rapidly, because we don't have to do any solution dilution. Solution dilution is not required here. However, solution dilution is required from the equivalence point on. You know, there we definitely have to do solution dilution. All right, so if we're going from the equivalence point, that's not too difficult. But what if we go the other way using the shortcut? It's not too difficult. What if we go this way? Let's say I want to know the pH at 9.9 milliliters. And so the next example is with 9.90 milliliters sodium hydroxide, what is the pH equal to? So this one, the way we do this is this. We just think we've neutralized 9.90 milliliters out of how many milliliters total? 10 milliliters. And so this much has been neutralized out of this much total. And so we call this a 9.9 out of 10 equivalence point, right? And so this is the 9.90 out of 10 equivalence point. And so what does that mean? Well, setting it up the same way we set up the previous problems, the pH is equal to pKa. Now, plus the log of the base. Well, what we've done is we've converted 9.90 out of 10 parts into base, right? Because we've neutralized that. How much do we have remaining? We only have 0.10 parts out of 10 remaining to be neutralized or unneutralized. And so what we do is we set this up like this. This is going to be the pKa plus the log 9.90 over 0.10, which is equal to
1.9.
what is it?
1.955.
Okay, 1.995, so this is the pKa plus 1.995. Okay, this is deviating from the pKa by 2 units. Is it still okay to use the Henderson-Hasselbalch equation for this?
No. Plus minus.
No, plus or minus 1 is to have an effective buffer. But we could use the Henderson-Hasselbalch over a much wider range. The only time we'd have to switch to ice is if we get very close to the equivalence point here, or if we're very close to the initial point here. That's when we have to use ice. And so even though we're deviating more than plus or minus 1, it's okay to use the Henderson-Hasselbalch because the assumption still stays valid over a pretty big range. It's just, this is going to be such a lopsided buffer, it's not going to be very effective. Uh-huh.
So you said that once you get closer to the equation, equivalence by my best.
Yeah.
And then what else?
Right at the initial point here. That's where the assumption, simplifying assumption fails, and we'd have to use the ice table instead of the Henderson-Hasselbalch. And so it's okay over a much wider range. To prove this to yourself, you can solve this using, the ice table and see. Uh-huh.
So how close is close enough for the HH equation?
Well, typically, unless it's like for your standard buffer problem, we aren't going to be using ice table. For your standard buffer problem, we're never going to calculate right here because we're just going to kind of interpolate, the curve through here. So we really aren't going to do that calculation. But how close? Like within like half a drop. If you're within a half a drop or something, then you might think about it. But within a drop, I'd still use the Henderson-Hasselbalch probably. And then maybe 1 drop after, I'd probably start using the Henderson-Hasselbalch. It depends on some concentrations. Or, you might be more conservative. This is, actually, this is 2 drops. 1/10 of a milliliter is 2 drops away. I'm still using the Henderson-Hasselbalch. So we're talking about fractions of a drop. Like maybe even half a drop is too big. Are you going to get do you actually really work at getting a tiny fraction of a drop suspended on the tip of the burette? Well, most people get it like a half a drop. The highest resolution. But anyway. What should we do next? All right. What we should do next. All right, so that's within 2 drops of the equivalence point there. Why don't you do this? Why don't you tell me what the pH is? Let's go with maybe about 5 drops in. So about 5 drops in. So the next example, let's go with like 0.25 milliliters of sodium hydroxide. This is just rough. A drop is about 0.05 milliliters. So we'll go with a 1/4 mil. What is the pH at a 1/4 mil in? 5 drops into this titration. Why don't you calculate that? Okay, you have it?
Okay, it's 1.59.
Okay, pKa minus 1.591. All right, you know, the pKa for this is 474, so let's just 1.591. Give us a pH around 3. 3.15. All right, so the buffer, those are typical buffer region calculations. We either go from, you know, the milliliters to pH, or we go from just the equivalence points to pH. All right, once we get to the equivalence point, then what do we have? We have a salt solution. Here we have to do solution dilution. And so that would be at 10 milliliters at the equivalence point. 10.0 milliliters of sodium hydroxide added to our 10 milliliters of acetic acid. This is going to give us a total volume of 20.0 milliliters. And then we'll just do the solution dilutions, just a 1 to 2 dilution. So this will be 0.0500 molar, and the acetic acid will be 0.0500 molar. And then we set up the ice table with strongest acid, acetic acid, reacting with the strongest base, sodium hydroxide. The same thing. In fact, we could do all the calculations, you know, even in the buffer region, like this. We're going to get sodium acetate in H2O liquid. K is very, very large. HAC is 0.0500, 0.0500, 0. And since this is complete, we'll see these two are going to go to 0, and we're left with 0.0500 molar sodium acetate. Then we repeat the same thing. It's the strongest acid plus the strongest base. What's the strongest acid in this case? Oops. Strongest acid is water. The strongest base is sodium acetate. All right, so let's do that next. Over here. So we'll just take our acetate plus water. This is going to give us HAC plus hydroxide. All right. This is a Kb, it's base plus water. Kb will equal Kw over Ka for acetic acid, conjugate acid. 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 Ka for acetic acid. It gives us our Kb. 0.0500 molar, this would be 0 molar and 0 molar, since there's no more acetic acid left to neutralize all of it. And so this is just a Kb. What do you think? Are we gonna, this would be step 1. What would step 2 be? What would step 2 be? Well, this would be the hydroxide. This is a base solution. So this would be the hydroxide from the acetate. And then in step 2, we'd consider the hydroxide from water. And so step 2 would be Kw, but what do you think about Kw? Would it contribute much?
No.
Probably not. Well, it depends on the Kv. Let's take a look. Maybe we'll figure this out here. What is the Kv for this? Yeah. 0.5 to the negative 9, or 5.55 times 10 to the negative 10. All right, let's go with that. We'll change, and so we're going to have 0.0500 minus x molar, and x molar. It's going to be x squared over 0.0500 minus x. We'll use that simplifying assumption, so we'll get x squared over 0.0500, and therefore x is equal to
Two point seven
2.77
seven.
times 10 to the negative
11.
11. Wow, maybe.
No square.
Oh, is that, okay. Take this
So
one. 5.26 times 10 to the minus 6. All right, so we have 5.26 times 10 to the minus 6 for our hydroxide. Should we worry about Kw? Molar. Would you worry about Kw? No. And Kw, maybe 10 to the minus 7, 10 to the minus 8, it's not really going to, probably it's going to be more like 10 to the minus 8, 10 to the minus 9 contribution. This is kind of getting bigger. And so we don't worry about it here. The hydroxide isn't there. And so we'll stop here, we'll calculate the pOH, and then get the pH from this. What do you get? 5.27. And that means the pH is, the pH, 8.73. Okay. The pH here, 8.73. All right. Now, let's go. Should we go 1 drop past the equivalence point? Let's try that. Let's go 1 drop past the equivalence point. So the equivalence point would be 10 milliliters. 1 drop past it would be roughly what? 10.05 milliliters. 10.05 milliliters of sodium hydroxide, that would be the equivalence point plus a drop, roughly. Let's figure out what the pH is. At the equivalence point, the pH is 873. You know, but is that a neutral pH? No, it's not a neutral pH, but have we neutralized the acid? Yes. Neutralized. It's just the salt that we form in this case is basic salt. If we go a drop past, what's going to happen? What's the pH going to go to? What do you think? Is it going to be right around 873? It's just 1 drop. There's 1 drop. Maybe Kw is going to be significant because, well, we'll see. All right, so here we got 1005. So we have to do our solution dilution first. And so the total here is going to be 20.05 mils. And then what do we have? We have our sodium hydroxide, which would be a 1005 to 2005 dilution, 1/100 molar, which gives us what? And then our acetic acid would be a 1000 or 10, let's just go 10 over 2005 dilution. I'm just trying to keep 3 sig figs here, being consistent. That should be a sub-5 times 0.100 mole. You have the concentration?
Sodium hydroxide is 0.0501.
0.50
0.0501.
0501. Give me one more digit.
9.
9?
2.
2? 5012? Okay. And the acetic acid?
0.0498.
4987.
7.
So, do this next. Strongest acid, acetic acid. Strongest base, sodium hydroxide. Going to produce sodium acetate. Some water. And then let's put in the initials. 0.04980. 4987, 0.04987, 0.05012, change, equilibrium. So we've neutralized all the acid. Nine, 7. So how much? 2, 12, 5. Point 0.00025. What you guys say? 25 molar. And then 0.04987 molar acetic acid. And so what we have here is a strong base, weak base solution. And so what we're doing is we got a mixture of bases. When we got a mixture of bases, we look for all the hydroxide ion contributors, right? Starting with the biggest. What's the biggest hydroxide ion contributor? Sodium hydroxide. So we would do the Kb for sodium hydroxide, but doing the Kb for sodium hydroxide would be hydroxide plus water gives us water and hydroxide. And so this is what we see is what we get as far as the hydroxide ion concentration goes. Now, if we have this hydroxide ion concentration, do you expect much additional hydroxide from sodium acetate? And look at sodium acetate is much more concentrated, isn't it? So sodium acetate is much more concentrated than sodium hydroxide. So shouldn't the sodium acetate contribute some? As we saw earlier, no. In fact, the strong base is going to dominate this. And, the only time we'd have to, this is with one drop, the only time we'd have to really consider it is in this red region here, right? Where we have, well, maybe much less than a half a drop. We'd have to have just a tiny fraction of a drop, right? To keep the sodium hydroxide concentration so low that the sodium hydroxide concentration is almost negligible, then it's all sodium acetate. And this will dominate. But should we just try it and see? All right, let's go ahead and try it because, okay, so sodium hydroxide, this is going to yield sodium ion hydroxide, and then Kb is the same, so this is soluble salt. And Kb is hydroxide plus water, yields water and hydroxide, so nothing really changes there. And so what we're going to be left with is, at the end of this, 0.04987 molar. And then we'll carry this down to the acetate. You know, acetate's going to contribute some hydroxide. And so this is going to be forming acetic acid plus hydroxide. So the acetate concentration is fairly high at 0.04987. This acetic acid is 0. The hydroxide concentration is 0.04. Yeah, that's right, 0.04987.
No, too high.
Oops, you're right. That's right. 0.00025. So the hydroxide is 0.0025 molar. So the change minus X plus X plus X. And so at equilibrium we get 0.04987 minus X, X, and 0.00025 plus X. So here, KB is equal to 5.55 times 10 to the minus 10, which is going to equal X times 0.00025 plus X over 0.04987 minus X. So we'll just try the simplifying assumption here. So this is going to equal X over 0.000, X times 0.0025. Divided by 0.04987, which means that X is equal to what? Times 10 to the minus what? 7. Okay, 1.10 times 10 to the minus 7. All right, so this is 2.5 times 10 to the minus 4. So if we add something 10 to the minus 7, will it really have any impact on this? No. And so this solution, the base dominates even one drop, after the equivalence point. Now, if we get more and more drops, then, for sure, the sodium acetate is negligible, the contribution of hydroxide. You see that? And so the next point we would calculate is at 15 milliliters out. At 15 milliliters out, this would be called the 3/2 equivalence point. At the 3/2 equivalence point, can we use the Henderson-Hasselbalch equation for that? At the 3/2 equivalence point. No, I mean, this is not in the buffer region. At the 3/2 equivalence point, this is just excess sodium hydroxide and sodium acetate. And so the calculation would be just like the one we just did, except we probably wouldn't do step 2 there for the acetate. For sure we wouldn't do step 2 for the acetate. Is that clear for this? What happens is the pH should keep climbing, but the pH really doesn't climb much. It kind of flattens out. Why do you think it flattens out? Because now, we're just adding sodium hydroxide, which is a strong base. We're adding sodium hydroxide, which is a strong base. Isn't it just kind of... in other words, this. If I keep adding sodium hydroxide, eventually, should I hit pH 14? Yes or no? If I keep adding sodium hydroxide, I'll hit pH 14 and then maybe go above 14? No. I can't. In fact, you know the pH, what is the pH of 0.100 molar sodium hydroxide? The pH of 0.100 molar sodium hydroxide is pH 13. Am I ever going to hit pH 13? It's impossible. I cannot hit pH 13. Why? Because I diluted it. Not until I get to infinite, sodium hydroxide, and then maybe that dilution is negligible, right? But I diluted it with the 10 milliliters of acid. I mean, I'm reacting some of the acid there. And so this is your basic monoprotic weak acid titrated with a strong base. Now let's take a look at polyprotic. Do 0.100 molar phosphoric acid. Let's do 10.0 milliliters. I want to keep the number simple. Titrated with 10.0 milliliters of 0.100 molar sodium hydroxide. I could make it more complicated. For example, one of the things I could do is I could make the concentrations different. If I make the concentrations different, then calculating volumes becomes a little bit more of a pain. But if I make the concentrations the same, then the volumes are very easy. Here. I start off at 0 milliliters of sodium hydroxide. Here's my pH. And so all I have over here is just phosphoric acid solution, 10 milliliters of it. And then in this region, what I do is I start to neutralize my phosphoric acid. So H3PO4 plus sodium hydroxide, NaOH. Now, how does sodium hydroxide work? If I add a drop of sodium hydroxide, that neutralizes, let's say, the first proton of this. If I add another drop, does that neutralize the second proton, or would that neutralize the first proton on a different first proton? In fact, I have to neutralize the first proton on all of them because the strongest base always reacts with the strongest acid first. It's not going to start attacking the second or the third proton until all the first proton is gone. And so this happens in a stepwise fashion. So here we're going to form sodium dihydrogen phosphate and water. And so here's our salt plus water. How many milliliters is it going to take to neutralize the first proton? Here. Completely. It's going to take 10 milliliters. And so at 10 milliliters here, I have salt. What's the salt? The salt is sodium dihydrogen phosphate and water. Before I hit this first equivalence point, I have what we call the H3PO4 and NaH2PO4 buffer region. Because I haven't neutralized all my phosphoric acid, but I did convert some of it into product, and this product is the conjugate base, so I have the acid conjugate base pair, which means at 5 milliliters, what is the pH? At 5 milliliters, the pH is equal to the pKa. Yeah, pH is equal to the pKa of phosphoric acid. I haven't neutralized my second proton. That means when I get to the excess base region up here, now this is normally excess base, but if I have excess base, what is it going to attack? It's going to attack the next strongest acid. The next strongest acid will be the second hydrogen, the dihydrogen phosphate. And so I actually don't get excess base here. What I get is this. I get my next acid, sodium dihydrogen phosphate, plus. Now it's going to be some of it's going to be neutralized by the base and converted into, actually I should write this up here. A little bit higher. So I have the sodium dihydrogen phosphate reacting with excess base, which is going to give me sodium monohydrogen phosphate and water. And so if I don't add enough base, then I'm going to partially neutralize the acid, which means there's going to be some acid left over, sodium dihydrogen phosphate. And some of that's going to be converted into base, which will be the sodium monohydrogen phosphate. And so now I have this region. So we're going to call this buffer region 1. This one will be buffer region 2. All right, at 20 milliliters, I would have neutralized all the, that is another 10 milliliter aliquot. And so this will be a total of 20 milliliters. A total of 20 milliliters, I would have neutralized all this remaining acid and converted it just to the salt. And so this salt would be sodium monohydrogen phosphate plus H2O liquid. Well, this is a triprotic acid. And so once I've neutralized all the second proton, now I'm going to neutralize all the third proton that remains. And so up here, I have some of the monohydrogen phosphate. And if I have excess base, the excess base is going to attack the monohydrogen phosphate to form sodium phosphate and water. Liquid. If I don't completely neutralize all of the third proton here on the acid, then I'm going to be in this region, which we'll call the buffer region 3, because I have some acid and its conjugate base, which would be sodium phosphate. So this is buffer region 3. Running out of room here. But at 30 milliliters, I would have neutralized all of it. And so at 30 milliliters, I should have salt, which would be just sodium phosphate solution. And so no more acid left. And if I go beyond 30 milliliters, which is off the board here, beyond 30 milliliters, I have excess sodium hydroxide, which is strong base, and sodium phosphate, which is weak base. So I have a strong base, weak base combo. I just look for all hydroxide ion contributors to that. All right, some of these points you could get very, very rapidly in this. For example, why don't you, let's say at 5 milliliters, what's the pH? The pH is equal to the pKa phosphoric acid. At what? 7.5 milliliters, what is the pH? This is the pH. The pH is equal to pKa plus 0.477. And so why don't you just map it out, the ones you can do quickly in buffer region 1, and then replicate that for buffer region 2 and buffer region 3. Okay, and so just go ahead and fill in some volumes and some pHs there. And then we'll look at doing some other calculations right now. All right, so it should be pretty quick, right? You guys see it? At 5 milliliters, the pH is equal to pKa. At 7.5, pKa plus 0.477. At, what is that? At 9.09 milliliters, the pH is going to equal pKa plus 1. At 0.909 milliliters, the pH is pKa minus 1. And so, what do we have here? At how many milliliters? At 15 milliliters, the pH is equal to the, the pH is equal to the pKa, but now the acid's different. The acid is H2PO4 minus. And so that's at 15. At 17.5, it's
0.4.
pKa plus 0.477. At 12.5 milliliters, it's minus 0.47. At 10.909 milliliters, it's minus 1. At 19.9, what is it? $909. 1909. At 1909 milliliters, what is it?
Plus 1 pKa.
Yeah. All right, then going over here, what are the pHs? I mean, pHs starting with the volumes. The first volume would be 20.909. At 20.909, the pH will be pKa 3 minus 1. At 22.5, at 25, pKa 3. At 27.5, plus 0.477, and at 29.9, it's plus 1. Does everybody see that? And so these points are pretty rapid. There are some other rapid points too, but before I do that, let's try a calculation. Let's try this on for what will be the pH at 2.42 milliliters? Not 12.42 milliliters. At 12.42 milliliters, what is the pH? Try that. Let's see. 12.42 milliliters, what is the pH? Okay. pH is equal to the pKa 2 minus 0.49. How did you get that? Yeah. And so you use the equation pKh is equal to the pKa plus the log. The log of what? Well, yeah, it's going to be 2.42. You see, we have to reset at 10. We reset at 10, so then the second equivalence point is going to take 10 milliliters. The first equivalence point took 10 milliliters. Second will take 10 milliliters. The third is going to take 10 milliliters. And so we reset at 10, therefore we're only 2.42 parts of the way. We aren't 12.42 parts out of the way for 20. It's 2.42 parts over 10. And so what we've done is we've converted 2.42 parts out of 10 into base, and that means we have how many more mils left? 7.58 over 10 left. And so that should give it. Was that pretty? You guys see that? All right, there are some other points that are going to be rapid too. Here it's a little easier because we don't have to reset. Just take it as is. For this third one, it's the same kind of deal. We have to reset it. The third equivalence region. The other points that are rapid is this. This is going to be rapid because you know what kind of salt that is? This is amphoteric salt. And so the amphoteric salt, we don't have to do solution dilution. We don't have to do an ice table. The pH is just equal to the pKa for the amphoteric, which is H2PO4 minus, plus the pKa for its conjugate acid, which is H3PO4, divided by 2. If we look at the second equivalence point, the second equivalence point is an amphoteric salt also. And the pH for this one will be equal to the pKa for the amphoteric salt, which would in this case be HPO4 2 minus, plus the pKa for its conjugate acid, which would be H2PO4 minus, divided by 2. That's the second equivalence point. And so the first and the second equivalence point are easy to get. The third equivalence point is more work because this is not an amphoteric salt. This is a tri-basic salt. Well, it's a tri-basic salt, meaning we have Kb1, Kb2, Kb3, and Kw. If we're only interested in the pH, do we have to do Kb2, Kb3, and Kw? What do you think? No. Probably Kb1 is enough. And so it's a tri-basic salt, but for pH, Kb1 should be enough. Should do it. And it does. And so here we have to do solution dilution because we need the diluted concentration of this salt. We're adding a lot of base here by the time we hit 30. Okay, then we go beyond that. Going beyond that, we're going to have now a tri-basic salt and excess sodium hydroxide. So, well, in other words, strong base and weak base. And we know that the pH is going to be dominated by the strong base, so we probably just look at the strong base and ignore the weak base because the weak base is such a minor contributor to the solution. And so do you want to do a calculation in that region? Or you want me to do a calculation in that region or not? Yeah?
Yeah.
All right. So how many mils should we go out to? Maybe 35 mils? We go out to 35 mils? So we'll go out to 35 mils of sodium hydroxide and figure out what the pH is here. I'm going to do it the long way first. There are short ways of doing this as well. But first step is solution dilution. So I'm going to have a total of 45.0 milliliters of solution here. So the sodium hydroxide will be a 35 to 45 dilution of 0.100 molar. The acetic acid will be a 10 to 45 dilution, 0.100 molar. Oops. Phosphoric acid. I start all the way at the beginning. Even though I'm past the third equivalence point, I just reset this whole problem right at the beginning. Do it from the beginning. It's easier that way, actually.
Didn't you say sodium phosphate?
We have, I'm actually starting over again. Yes, it is sodium phosphate, right? But I'm starting the whole problem from the beginning, starting with phosphoric acid. It's actually easier that way than trying to do it at the end. Because the reason it's easier just to start it from the beginning, each titration problem you start from the beginning because that way you only use one method to solve all problems. Even if you don't know all these shortcuts, what you could do is you could just start it like this. Step A, solution dilution, right? Do the solution dilution, then step 1 is strongest acid with the strongest base. So we got H3PO4 plus sodium hydroxide, which is going to give us sodium dihydrogen phosphate plus water. What are these concentrations here? What is it? 077? 77? 7? One more. 7. Okay, and then this one?
0.0222.
Quadruple 2 and quadruple 7? And 0. So the change is going to be complete, so we lose all our phosphoric acid. We got 0.07, not 7, so we got 0.05555 molar left, and then 0.02222 molar here. Oh, is this a buffer solution? We have a base now. This was actually this is acid going to conjugate, but now this is amphoteric. So this could be our acid. This is our base. Is this a buffer solution? No, because they aren't conjugates to each other. And so this is step 1. What's step 2? NaOH plus, okay. Right. And so the strongest acid is going to be NaH2PO4. Strongest base is sodium hydroxide. This is going to give us Na2HPO4 plus water. Change should be complete. It's going to be So the H2PO4 is 0.02222 molar. Sodium hydroxide is 0.05555 molar. This is 0 molar. Initial change. We're going to consume all this. That's going to go down to 0. This is going to give me 0.03333 molar and 0.0222 molar. Okay, I have, again, now, this is not a buffer. I'm going to take the strongest base and the strongest acid and react them. This is my next step. Sodium Na2HPO4 plus sodium hydroxide. And this is just neutralizing the third proton on our acid. And this is going to give us sodium phosphate plus H2O liquid. So initial change in equilibrium. This is going to be 0.02222. Sodium hydroxide 0.03333. This is 0. The change is completely neutralized. This is going to give me 0.01111 molar and 0.0222 molar. All right, so now I'm left with a strong base and a weak base. This is not amphoteric. I've neutralized all the hydrogens. So if I have a strong base, weak base, then I've got to look for all the hydroxide contributors starting with the biggest. The biggest will be sodium hydroxide and then go smaller. And so the question again is, will sodium phosphate, do you think, contribute much additional? No. No. I would think this would be a minor contributor. And so I'd stop here, calculate the pOH, and then determine the pH. That's how I do it. Is that good? All right, so let's do a couple more since let's start chapter 18. I was going to start it today, but all right, the couple more is this. pH of 2.00, how many milliliters of sodium hydroxide will I have to add? Get to a pH of 2.00. Well, that means we need certain numbers here. And the first numbers we need is what region are we? And so what region are we? In order to figure out what region it is, we need the pKa values. So do you know what pKa1 is? 2.15. So pKa1 is 215, pKa2 is 7.20, pKa3 is 12.38. And so what region do you think we are? We're at the pKa1 minus 0.15, right? You see that? And so we must be in buffer region 1. And so go ahead and figure out how many milliliters it's going to take. Does somebody have it? 5.854 milliliter. All right, so let's just go through it quickly here. So the pH is equal to pKa1 plus the log of the ratio here. And so we already know what the pH is. The pH should be 2.00, which is going to equal to pKa1 plus the log of the ratio. And then subtract that from both sides and get the ratio. We get the ratio is equal to 10 to the minus 0.15. Is that right? And so the ratio comes out to 0.7079. That's the ratio. And so what we do here is we want to figure out what equivalence point are we at? You know, what fraction of the equivalence point are we at? And so this ratio is 0.7079 over 1. Does that mean we're at the 7.7 over 1 equivalence point? Or the 7/10 equivalence point? So is this the 7/10 equivalence point? No. It isn't. A lot of people make that mistake. This is not the 7/10 equivalence point. This is 0.7079 parts of base over 1 part of acid. And so we have to still neutralize this 1 part of acid. We only neutralized 0.7 parts. How many total parts of acid were there? Okay, so what this translates to is that we had 0.7079 out of 1.7079 total parts. This would be the base. This would be the acid. And that is, we're going to have 1 part left over of acid over 1.7079 parts total. So this is the acid. And so it's actually what we call the 0.7079 out of 1.7079 equivalence point. This is the fraction. So we're less than halfway. Is it 4.50?
7.
And so we know this goes from 0 to 10. And so this would be the 10/10ths equivalence point. This would be the 0/10ths. And so where would it be? Well, the 10/10ths is 10 milliliters. And so what we do is we just take 0.7079 divided by 1.7079 times a total volume of 10 milliliters, which gives us 4.147 milliliters. That would be. So this is the tricky part here. This is the part where most people fail. They fail to convert this here. And so this is critical. All right, are we okay with that? All right, now on this one. Yeah, all right. Let's stop here.